Hello, GopherCon. My name is Derek Parker, and today I'm going to be talking to you about how to deterministically debug your Go programs using Delve. Now, before I get into any further introduction of myself or the content of this talk, I'd be remiss if I didn't first introduce some of the associates that I have joining me on stage today. To my left is a portrait of myself painted by my wife. To my right is a gopher kind of awkwardly nailed to the wall. Now, no gophers were actually harmed during the making of this video. The nails to the tag, the gopher is perfectly fine. Secondly, let me say a huge thank you to the organizers of GopherCon for turning this event into such an amazing virtual experience. I know with all of the craziness that's happening this year, we can't actually get together in person, but the fact that the GopherCon organizers were able to overcome all of that and still put on an amazing event says a lot about them and about the community in general. So huge thanks to them and huge thanks to the community for supporting the conference and for everyone who is viewing my talk right now. I really appreciate it. Okay, now with some of those formalities out of the way, let's get into a little bit more introduction of myself. So as I mentioned already, my name is Derek Parker. I am a senior software engineer at Red Hat, where I work on upstream Go development and maintenance and development of Delve, which is the Go debugger. You can reach me on Twitter at @DirkTheDaring, and I'm also at GitHub. The links to both of those will be provided on the final slide at the very end. Now, enough of the formalities, enough of the introduction. Let's actually start talking about the content that we're all here to actually see. Deterministic debugging. This is a phrase that I think is not used very often, and that's why, in part, I'm so excited to give this talk. I think that this technology and this use case for debugging is extremely underutilized, and it's a technology and it's a debugging process that can help you in so many ways, especially dealing with intermittent bugs that may not make themselves known every time you run the program. Maybe they only show up 1 out of 100 runs or 1,000 runs or something like that. Are you really gonna just repeat execution of your program 1,000 times until you hit your bug? And then what happens when that debug session ends? You have to do it 1,000 more times until you hit the bug and you can try to fix it? Deterministic debugging is a concept that tries to alleviate all of those issues. I'll get into the technical details of how this is actually accomplished, but first I just kind of wanted to introduce the phrase a little bit. Now, one more little bit of formality actually, before we continue with the rest of the technical portions of this talk. I would like to first give a huge shout out to the co-maintainer of Delve, who worked on the bulk of this work. I'm happy to talk and brag about it, and I was happy to do all of the code reviews, but I absolutely have to give credit where credit's due. So thanks a lot for the work and for all of the contributions that the entire community has made to the Delve project so far. Now, let's talk about what is deterministic debugging. Now, some of you may actually be familiar with this little character that I have on the screen right now, but for those of you who aren't, my 1-year-old is extremely into Toy Story 4, and Forky is one of the new characters introduced, and part of his whole shtick is that he doesn't know anything, so he asks, what is everything? What is this? What is that? What is that, right? So it seemed appropriate, since we're asking what is deterministic debugging, to have this little guy up on the screen. So let's dig into this question a little bit more. What is deterministic debugging? I think that before going into all of the technical details, a good way that I like to relay this information and that I like to kind of express it to folks of what this concept is and what it's all about. I think the best way to describe it is, if you've ever seen the movie Groundhog Day. Now, If you've never seen the movie Groundhog Day, let me explain it to you a little bit, and you'll see why it's relevant. So Groundhog Day is a movie where Bill Murray goes to Punxsutawney, and on Groundhog Day wakes up, and then the next day he wakes up and it's still Groundhog Day, and so on and so forth. And every day he wakes up, and wakes up, and it's still Groundhog's Day. Nothing has changed. Anything that he did the day before, all of the consequences of those actions are completely wiped out. And he starts the day exactly the same as he did the day before. Everybody he interacts with is reset. Nothing carries over from the interactions and experiences that Bill Murray's character had the day before. So why is that relevant? It's relevant because that's kind of what deterministic debugging is like. The whole point is for every debug session to be perfectly deterministic. Now, this means that every time you run through this program and debug it this way, it's going to behave exactly the same as it did the last time that you debugged this program, and the time before that, and the time before that, and the time before that. Every single time you run this program debugging this way, it will exhibit the same exact behaviors. It will exhibit the same exact bugs. Everything will be as faithfully reproduced as possible from the first time that this process was executed. Now, how is that possible, right? That seems like seems pretty exciting and very, very useful. Why aren't we doing more of that now? So that's kind of what this talk is about. I want to introduce just this concept in general, and then get into some of the technical details of actually how is this possible on a little bit of a lower level. So the trajectory of this talk will start off as it is, pretty high level for right now. Then we'll get pretty into the weeds for a little while as I go through some of the back-end implementations, some of the technical details that makes this actually possible. And then we'll go back up a little bit and figure out how to actually use this to your benefit, to all of our mutual benefit. So the way that this is actually possible, how do we replay something? How do we debug the same exact process time and time again through multiple debug sessions and all of this stuff? How do we remove all of these sources of non-determinism so that every single time we are debugging a process that exhibits the same exact behavior? And the behavior that we want it to exhibit is likely the bug. And again, I mentioned the bug that may only show up one every 100 or 1,000 runs or something like that. The way that this is possible is through technology called record and replay debugging. Now, this is pretty simple. It kind of describes itself. Record and replay debugging is essentially the process of recording the execution of a process in some way and then being able to faithfully reproduce that execution an infinite number of times. So, from a technical level, how is that actually possible? Well, when recording a process, there's certain ways where we can record some of the sources of non-determinism. And those recordings, the recordings of that non-determinism, can be played back while the process is being run again. And there's certain other features of a process that can be set up, recorded and set up exactly as they were during the initial recording, the first time the process was actually executed. There's a lot of technology underneath the hood that makes this work, all up and down the stack, from the Linux kernel to user space and back. Technologies like ptrace, eBPF, even down to the hardware performance counter registers. There's so many things that come together to make this possible. And that's exactly what the first portion of this talk is about, kind of taking a deep dive into how is this all possible? What are we really doing behind the scenes to make this work? It's kind of low-level details that you don't really need to know to actually be able to take advantage of and use this technology, but I'm always fascinated by deep dives, and I think other folks might be too. So hopefully this portion is as interesting to you as it is to me. So let's go and first talk about different kinds of ways to record processes and things like that. We'll go over some of the pros and cons, and then following that, we'll pick our favorite, and then we'll take a deeper dive into how that particular piece of technology operates behind the scenes. So there's a few different types of ways of recording, what the execution state that's happening. So the two main are virtual machine recording. It's exactly what it sounds like. You're recording the execution of an entire virtual machine, essentially. And the second is user space recording. So you're above the kernel, you're in user space, and you're recording maybe just a process tree or something like that. So with virtual machine recording, you have a few different options there. I've listed a few on the slides. User space recording, you also have a few options as well. So let's talk about some of these implementations and some of the pros and cons that you might face. So nothing is perfect. This technology, even the piece of technology that I'll be speaking about the rest of this talk is also not perfect. There's pros and cons to everything, and there's some caveats. But let's take a look at some of the problems with the implementations that we just previously discussed, VM versus user space. First, let's talk about VM recording. So one of the major cons, as I see it, is that it's virtual machine recording. So you have to be recording within a virtual machine. That may not always be ideal. That might not always even be possible. What if you want to record something that's happening on a production server or a staging server or something like that that's not running the virtual machine that supports recording? That can be a lot of problems. Or what if you are running that on a server or something, but you don't have access to it on your local laptop, your local hardware, to actually do the debug session locally? A lot of problems there. They also produce really, really large traces. If you think about it, recording the entire execution of a virtual machine consists of recording the kernel, all of the other processes that are running. There's so much noise there that these traces can be really, really large, and getting to what you actually need could be rather difficult. Finally, it's not really a widely supported option. There are a few vendors that do support it, but it's not very widely supported, and usually it's proprietary. I don't know of like Vagrant or anything else like that would actually support this. Moving on, let's talk a little bit about user space recording, because hint, that's kind of what we're going to be focusing on for the rest of the talk. So there are still some downsides of user space recording. The first being, you're not actually recording the kernel execution. Is that important? It turns out not so much. What we can do to get around, recording everything that the kernel is doing is actually being a little bit smarter and just recording the results of our interactions with the kernel. We don't need to know everything that the kernel is doing. We just need to know the results of our interactions with the kernel. So the results of syscalls and things like that. So maybe not so much of a con. The next potential downside is that some of these solutions require like code instrumentation, something that I'm not a huge fan of, but something to kind of keep in mind. Now, the solution that we discuss going forward does not require this. It does no code instrumentation at all whatsoever. But that is a downside of some of the other options that are available right now. Lastly, some of these user space solutions also require kernel extensions, which kind of reduces portability and things like that. So a few downsides, there's a lot of downsides. This is not a lot of downsides, but all we've talked about so far are downsides. A lot of negativity. This all sounds terrible. So why? What's the solution? Why do we use this? So it turns out that there's actually a really good solution, a good middle ground for all of these problems. Skip the slide. Okay, so the solution for now is Mozilla RR. So for those of you who are not aware, Mozilla RR is what's called a record and replay type debugger that came out of Mozilla, right? Delve is actually able to use RR and coordinate with it so that you get the power of the record and replay deterministic debugging with the power of Delve and its knowledge of Go programs. So Delve kind of defers to Mozilla RR for some of the recording and the replaying of the actual process. Delve uses RR as kind of a backend and is able to interface with it and still, as I mentioned, supply all of the great features that are present in Delve that are the deep knowledge of Go internals, type system, and everything like that, runtime, all of that stuff. It can still bring all of that power to this other backend, this record and replay backend, and I think that's really, really exciting. So after getting through some of the kind of technical parts of how this works, we'll get a deep dive into how to actually use this from the Delve perspective. But those are kind of how the pieces fit together. So what we're really trying to do with record and replay debugging is essentially we want to eliminate the sources of non-determinism. Now, how do you do that? I mean, there's a relatively lot of things that can be non-deterministic about running a process on hardware, on a computer, on various operating systems. There's a lot of things that can happen between different runs of your process that are potentially out of your control. So how do you record all of this information and how do you replay it back faithfully? How do you get rid of all of this non-determinism? So the way to do it is to kind of first identify the sources of non-determinism and then intercept and record the results of that, right? So let's take a look at some of the sources of non-determinism that we can actually control. The first is certain CPU instructions. So certain CPU instructions are non-deterministic, right? A lot of them are very deterministic. You give them inputs or whatever, they can act on that. They store the result of it in another registry or a memory address somewhere, or something like that. Every time if you give them the same inputs, they're going to give you the same output and store it in the same place, especially if it's register storage or something like that. But there are some CPU instructions that are inherently non-deterministic. So how do we deal with those? For example, there's the rdrand instructions, which generates random numbers. Hopefully this is non-deterministic on your system. Turns out that it's not used very widely. A lot of programs prefer dev random and things like that. So it can be patched out of programs that use it. Not a huge deal. There's also rdtsc, which reads a timestamp counter. This instruction can be trapped. So what a trap means is when this instruction is executed, the kernel will actually let us know in user space, and we can kind of do something to handle that, and then continue execution. So whenever I say trap, it's basically the kernel telling us that something happened, user space reacting to it, and then typically we go back to the kernel. So finally, there's also CPU ID. So that can return. It's mostly deterministic, but it can also return the core number that your process is running on, or something like that. And that can be a source of non-determinism. So that's another one that can also be trapped and recorded on newer Linux kernels 4.12 and above. So that's pretty much it for CPU instructions. It turns out they're mostly deterministic. There's a few that we kind of had to take care of. Another one that gets kind of tricky is thread scheduling. So think about, we're Go programmers. You're running multiple threads in your process, and the parallelism and the concurrency is one of the big things that brought us all to Go in the first place, I would imagine. I know for me, it was one of the big draws. So how do we handle recording thread scheduling, the Linux, the kernel scheduling our threads and things like that? How do we record all of that non-determinism? As I mentioned earlier, we're not recording the kernel. So what do we do? So it turns out RR under the hood ends up running everything single-threaded and implements kind of its own user space thread scheduler. It does pay attention to thread priorities and all of that good stuff, but the benefit being that having a user space scheduler managed by RR allows that thread scheduling to be more faithfully played back during the debug session, and this is super important because the order of operations and thread scheduling and all of that stuff that needs to be faithfully reproduced. You can't have threads executing different times, being scheduled different than when they originally were. If that is a cause of your bug, you may miss it when it's replayed, and that's not. We can't have that. So thread scheduling is another big one. We also have system calls. So, various system calls can return different kinds of data, right? That, they return file descriptors, memory mappings, all kinds of stuff, data in registers and memory and shared and syscalls can return data using registers and memory and all kinds of stuff. There's tons of non-determinism that can potentially happen from making these syscalls. So this one is actually pretty easy. Using a combination of ptrace, which, if you're not familiar with ptrace, it's a Unix-like feature of the Linux kernel. The Darwin kernel also has some ptrace availability and things like that. But essentially, it's a way for you to spy on other programs, essentially, and it's a foundation of how most major debuggers work. So if you'd like to dig a little bit into that, there's always man ptrace, or I would encourage anybody who's interested to take a deeper dive on that subject. However, ptrace for capturing syscalls can be it can have some performance penalties. So instead of always using ptrace, RR is able to put in these shims that end up recording the result of these syscalls without having to do so many context switches between user space and the kernel and so on and so forth when you're doing all of these ptrace operations. So the recording of the process ends up being a lot more performant in these cases, where a lot of these syscalls won't actually slow down the performance of your process by that much, right? And that's a big thing if you actually want to try recording a process in staging or record something in production. The performance penalty is something to be aware of. Also, the memory layout of a process can be different, right? Where variables are allocated, where everything lives in memory. This is kind of a source of non-determinism that we can also record and replay. And this means that every time you execute the program, your variables are going to be located at the same address. Your memory layout, all of this stuff is going to be exactly the same. So if there's something with the memory or the memory layout or something like that that's causing issues with your problem or causing problems with your process, this can be recorded and played back, and you can find these classes of bugs as well. There's also shared memory. So shared memory is a pretty big source of non-determinism. It's alleviated somewhat by RR having its own thread scheduler, and what RR does on top of that is in the thread scheduler, only one thread is actually scheduled at a time. So for highly concurrent parallel programs, this could be a performance hit as well for a lot of Go programs. But again, it's something that could be, it's something that could be, you could put up with if your goal is to just debug. This isn't something where you would be constantly recording all of your production processes and stuff like that just yet. However, with the RR thread scheduler running, essentially the program single-threaded, we avoid a lot of the shared memory issues between threads and things like that. And also, there's shared memory with things like Xserver and Pulse Audio and stuff like that on Linux. But that kind of stuff can be patched out. So there's workarounds for that as well. Now, finally, we have signal handling. Signals can be delivered to your process, at all kinds of different times. So how do we actually record and replay that? So it turns out that we can, with a combination of P-trays and hardware performance counters and things like that, we can faithfully record when a signal was delivered to your process, so that we can then it can then be redelivered to that process when it's being played back, just in case signal handling plays an issue in your bug or anything like that. This is another source of non-determinism that can be recorded and faithfully replayed. Now, let's talk a little bit about some sources of non-determinism that we cannot control. So there's only a few of these. It turns out that, we can't control or record the stuff that's happening outside of user space. As I mentioned earlier, RR doesn't do any kind of kernel recording or anything like that. It's only your user space process tree. So that turns out to not actually matter for the reasons that I mentioned earlier. As long as we're recording the interactions with the kernel, we don't actually need to record what the kernel is doing. We just kind of need to treat it as like a black box and record the information that comes out of it. And then once we have that, we can go ahead and replay it at a later time, and we really don't have any issues there. Now, trickier is hardware failures. We're not going to make your hardware fail if it fails during the recording of your process. And so that's just a source of non-determinism that can happen during the execution of your program, but it's not something that we can reproduce when you replay the execution and try to debug what happened. So let's talk about pros and cons to this approach. Pro, low overhead. There's no virtual machine. There's no kernel modifications. There's no code instrumentation. It's pretty lightweight. And with some of the workarounds for syscall recording and things like that, it's pretty efficient as far as recording. I don't have the numbers in front of me right now as far as the percentage, and your percentage overhead may vary depending on the load that you're running when you're recording and things like that. But the whole process tries to be as efficient as possible. Now, obviously, there's going to be some sort of overhead, but tries to be as efficient as possible. Another huge pro is that it can faithfully reproduce bugs. Now, this is a huge issue. If you have a bug that, like I mentioned, only reproduces every 100 or 1,000 runs, or only reproduces in very niche or certain circumstances, if you can record that failure once, you can replay it faithfully over and over and over again. You can even take that recording and share it amongst your teammates and things like that to get some collaboration into how to fix this issue. And I see that as a huge pro. You can record a trace and replay it anywhere. I kind of touched on it a little bit during this last part, but essentially, if you record a failure on a server or on your machine or something like that, and you just need some help figuring out what's going on, or you record it on a server and you want to debug it locally, or you want to send it out to a coworker or somebody else to help debug, you have this artifact that you can kind of ship around, and this is really important and powerful. Because, like I mentioned, you can debug anywhere you want, essentially, and you can also kind of make it a little bit more collaborative by, if you can't figure it out, sending it off to a colleague or something like that, and kind of sharing some of the debugging around. Another cool pro is that you can actually end up executing the program in reverse. So since the whole execution of the process is recorded, what you can do is you can reverse that execution. So if you needed to back up to a certain point in time while you were debugging your process, or you wanted to restart it from the beginning, or just go back a couple instructions, or go back a couple line numbers or something like that, all of this is very easy to do and very possible. You can also replay from the beginning and execute the same sequence of events. So you can set like kind of points to go back to. You can restart from the very beginning. You can go back to a certain branch or something like that, and every time you return to that point, from that point on, you're going to be experiencing the same thing. So it's very, very powerful for kind of iterative debugging. And I went too far. Okay, let me back up, a couple stack frames, or let me back up whatever, and kind of start exploring again from that point. It's a very powerful tool to use kind of while you're doing iterative debugging and trying to figure out what's going on. Now some cons. As I mentioned, highly parallel programs will experience some performance hit, right? I mean, with everything running essentially single-threaded, and the user space thread scheduling and all of that, you're gonna hit some performance overhead. Now, depending on your workload, the amount of overhead that you will experience can be vastly different, right? And the biggest thing to keep in mind is this is really kind of like a troubleshooting thing, right? So the performance overhead, while definitely a con, I think can be negligible in a lot of situations where maybe you're just recording a process on a staging server, or you're recording maybe even a process in production, but it's 1 out of 10 that are load balanced and something like that. Or you're just recording something locally, and you're recording it because it fails intermittently, and you want to capture that one time that it actually does fail. So definitely a con, but not the worst thing out there, I think. Another bigger con, I think, is that right now Mozilla only supports Linux. So it uses various features of the Linux kernel that are somewhat less portable, and so you have to have a Linux environment to run on, and there's a few more limitations there, which I'll touch on as well. The next big one being RR currently uses performance counters for a lot of things, but for figuring out when to deliver a signal to a process and all of these things. And access to these hardware performance counters aren't always exposed to all virtual machines. So you have to keep that in mind, where even if you have a Linux environment running in a virtual machine, sometimes it still might not work correctly. And this is just an unfortunate limitation that is slowly being alleviated via different virtual machine vendors and even on cloud-based providers and things like that. It's slowly becoming less and less of an issue, but still something to keep in mind. Okay, now let's move on to part 2. Now that a lot of the technical discussion is the deep dive of how all of this stuff works is a little bit over, we'll talk about how to actually use it and how you actually use it with Delve. Now, if any of this information that I just went over is interesting to you, or you want to dig into it more, I would definitely recommend taking a look at the Delve documentation, taking a look at Mozilla RR. There's a white paper on the project's website that kind of goes in a lot of detail about some of these lower level implementation details that I have discussed right now in the talk. So if you want to go even further than the level of detail that I've been able to go into during the course of this talk, I very much encourage you, look at Delve, the documentation, source code, look at RR, and read the paper about how it all works if you're interested in the record and replay stuff. So now, without further ado, let's talk about how you can actually use this. Let's talk about how you can use it with Delve. So as mentioned, Delve can interface with RR, and that allows Delve to leverage all of the power of RR while the user is able to leverage all of the power of Delve when they're debugging their Go programs. So it's kind of the best of both worlds. Now, how do you use it? First, as I mentioned, be using Linux. Now, the trick with the performance counters, that comes into play here, where certain virtualized Linux environments may not actually give you access to the performance counters, so it may not work. Typically, it's best if you have Linux actually running on real hardware, but the running RR under virtualization is getting better and better, and hopefully soon won't be an issue. But for the time being, you do need to be running on Linux, then you'll want to install Mozilla RR. So you can get pre-built binaries from their releases page, or you can go ahead and build from source. It's not too difficult to build from source if you need to. And I believe the official GitHub releases have dabs and RPMs and tarballs and all kinds of stuff that you can use to install. Right. So now, how do you use the RR backend with Delve? So there's three-ish ways of using this feature, this record and replay feature within Delve and with your Delve workflow. So the first option is the most work. So this is probably not the option that most people will use, but just to know that it's available, I think could be very powerful. So let me break this down a little bit. So at the very bottom, you see DLV replay. Now that's a command that can replay a recorded trace that already exists. So let's say you just have RR. You don't really need Delve for doing the recording. The power of Delve comes when you're debugging, when you're actually debugging the recording, right? So if you just had RR on a machine or something like that and you record a trace, you can take that trace, take it wherever you want, and you can debug it using this replay command. So I've shown a few examples, commands of what you can do. So you can build a binary, and those flags turn off some optimizations, which make debugging a little bit nicer. You can use RR to record that binary, the execution of that binary. What it'll do is it'll take that, it'll put the trace into a file somewhere to let you know where it is, and then you can use Delve to replay that trace and do the debugging. Option number 2 is a little bit more familiar, I think, to people who are more comfortable with Delve. So here we can just use the debug subcommand with a backend flag of RR to activate the RR backend. Now, what this does is essentially everything that I showed in the last command, but in one single step. So it'll compile your program for you in a way that's most optimal for being debugged. It will run RR and record a trace for you. Then it will spin up a debug session with Delve, debugging that trace that it just recorded. So all of those steps in one easy-to-use command that's already familiar with people who are already using Delve. Now, lastly, this one I think is most interesting because it shows off some of the power that you can do with Delve and the power of recording. So you can combine the power of scripting Delve with the power of record and replay to track down very hard to find bugs. So taking a look at this example that I have on the screen. So Delve is scripted by a language called Starlark, which is a Python, a language similar to Python that came over from the Bazel configuration system. Now you can use this language to script Delve, and what this command does is it will essentially, on your behalf, it will continue replaying and recording your program until it hits an error. And once it hits an error, it will stop replaying, and you will basically be debugging your recording, right? So instead of running Delve 100 times or running RR 100 times yourself at the command line, or writing your own, a bash script or something like that, you can script Delve to do it. And as soon as it hits the issue, you're already in a debug session where you can start figuring out what's going on. You already have a recording that you can, all of the benefits of having that recording, and you don't have to kind of run Delve or your process a bunch of times. This script will take care of doing it for you. So this is something that this isn't like a script that's baked into Delve or anything like that. This is just an example of how you can use the scripting power of Delve combined with this kind of record replay concept to basically let the computer and the debugger do some of the work for you. All right, so now let's get into a little bit of demo. So I just want to show off a little bit at the command line, kind of what some of the power of using of Delve in this way. So if we take a look here, we have a little program. And it's not doing a ton, but it is doing some time calls. It's getting the current timestamp. It's opening up dev random, and it's reading 16 bytes from it, and printing that information out. All of this stuff is information that would be very non-deterministic, right? It should be different every single run, and we can even verify that by running this a few times. So hello GopherCon 2020 timestamp, and we have 16 bytes that we've read from dev random. Now, obviously the year is still the same. We're still in 2020, but you can see the timestamp is different, and the bytes that we've read are different, right? And that's how it should be. Every single time that information is going to be a little bit different. So how do we make it not different? So let's go and do our Delve debug command. So right away you see some output, right? You see the output that, some Delve output. You see some RR output where it's telling you where it put the recording that it made. And then you're seeing the program output, right? So you can see hello GopherCon 2020. You can see this timestamp that we have here, and then you see our 16 bytes that we've collected. So as I mentioned, now we are in a debug session at the top of the recording, right? So we can just continue, and if we just continue, it just replays the recording, right? And we can see that from the first execution, the timestamp is exactly the same. The bytes that we've read are exactly the same. And if we restart, and you can just ignore the noise that's up on the screen right now, but if we restart and we continue, you can see still the bytes that we read are exactly the same. Everything, the timestamp, everything is exactly the same. So if we poke around this program a little bit, set a breakpoint, let's continue, right? Take a few steps. So we can do stuff like, let's print year, right? Year is 2020. Okay, it's 2020, every single time because we're still in the same year. But what about if we print the address of year? Okay, so we have this right here. This address, pretty normal. So what if we were to kind of go back and do some of these steps again, right? we've restarted the program. Now we're back at the breakpoint that we were at before. Let's print the address of year again. So you can see BD60, right? The last four, BD60. So you can see here the original address. After we restarted the program, the variable has the exact same address. So all of the memory layout, all of the information that we're getting back from, reading dev random and getting the current timestamp and all of this stuff, they've all been recorded and are being faithfully replayed during this debug session every single time that you debug your program. And with that, that is the end of my talk. I hope that everybody watching it enjoyed it. I hope that the technical aspects were interesting enough, and encourage anybody to read into this stuff a lot more and just try this feature out. Try it out on your day-to-day debugging, on your day-to-day workflow, and see if it helps. And if you're interested in it, we're always looking for contributors to delve, and there's tons to be done in the debugging space. So always things to do. So again, thank you very much for watching this talk. Thank you for the GopherCon organizers. Again, my name is Derek Parker. My GitHub and Twitter are on the slide as well if you want to look me up. Till then, thank you so much.